Lesson 12 is on electric potential energy and voltage. Two very important concepts. The lesson starts off by reviewing gravitational potential energy. So let's quickly do that. And recalling what we learned from Physics 20, we know the gravitational potential energy is energy based on location. So if an object is sitting on the ground, it has zero potential energy. If we lift it up a little bit, then it's going to gain some potential energy. The higher we lift it, the more potential energy it gets based on this formula here, EP equals mgh. So the greater h is, then obviously the greater the potential energy is. Okay, and that formula is derived from these two formulas that we learned in Physics 20. Force equals force times distance. Force equals mass times acceleration. Therefore, we can substitute this mass times acceleration in over here and get F equals MAD. And really, for gravitational potential energy, well, we also know that work equals the change in energy. And so that's how we end up with EP equals M, and the acceleration, we're talking about gravity, becomes G, and the D is the height. So that's how that formula comes about. Okay, now on to electric potential energy. And it's a very similar concept with just a few little tweaks. And before we look at the diagram here, I'm actually going to just do my own diagram at the bottom, just because I like to first introduce this concept using vertical parallel plates so that you don't get electric potential energy confused with gravitational potential energy and think of up and down, and when something's on the ground it has no potential energy. So let's say that we've got two vertical parallel plates that create a uniform electric field, right? And let's say we put a proton right here, something positively charged, and then we ask ourselves, does that proton have any electric potential energy? And the answer is no, it doesn't. It is at home right where it belongs because it's attracted to the negative plate. So it's just going to stay there just like I'm standing on the ground right now, quite comfortable. I have no incentive to go anywhere whatsoever. However, if a crane comes and holds me up 5 meters in the air and then lets go of me, then yes, I have incentive to move to the ground. So in other words, as we move this proton towards the positive plate, it is gaining electric potential energy, and we just call it EP because it's potential energy, right? Same as EP equals mgh, and EP is also electric potential energy. So we have to do work to move it because now we're moving it against the grain. It doesn't want to go to the positive plate. It's repelled by it in the same way that it takes work for the crane to lift me up off the ground. So that's the basics of what. Now let's just do another example. What if I put an electron? Let's go right here. If I put an electron right here, okay, does this have any electric potential energy? And the answer is yes. So let's review. So here, should be in green. Here it has zero electric potential energy. And over here, it has some value. We don't know what it is. It could be anything. For the electron here it has lots of electric potential energy because it's going to be repelled by the negative plate, so some value. And then once it gets over here, then that electron is going to have zero potential energy. So I just wanted to do those with vertical plates just so you don't get them confused with gravity. Gravity, of course, does play a factor, but it is such a minor factor. If we look at this example that's in your notes where we have a proton and at the top here it has high potential energy, not because it is above the plate, not because of gravity, but because it is being repelled by the positive plate here, right? And the positive plate repelling that positive charge, let's say it's a proton, is going to be infinitely stronger than the gravitational force pulling it down. So in this case, yes, the electrostatic force is down, the gravitational force is down. But let's say that this gravitational force, let's just say for the argument it was 1, this would be something like 1 million. Right? So the electrostatic force is going to be way stronger than the gravitational force, to the point that the gravitational force is actually negligible, doesn't have an effect on the problem. Okay, now what are we going to do? We need some formulas for this. We need a formula in the same way that we had this formula for gravitational potential energy. We need a formula for electric potential energy. And how are we going to get that? We're going to do it the same way that we got the gravitational potential energy. We're going to start with work equals force times distance. Now, here's the formula that we learned in earlier lessons. Remember, this is just like F equals ma. This one is just Fe equals EQ, right? In F equals ma, you have the force is calculated by the mass of the object and this acceleration in that field. If in Fe, the force is calculated by the charge of the object and the strength of the electric field that it is within. And then we do exactly what we did over here. We ended up with this, W equals MAD. We do the same thing here. We substitute this EQ in to right there, and we get this formula here. Okay, so this is a derived formula that is actually not on your formula sheet, and we can use it to solve these problems. A positive charge of 2.3 coulombs, 2.3 times 10 to the negative 6 coulombs. So let's just pound through these. Is between two parallel plates. It is close to the negative plate. The electric field between the two plates is, so where they're giving us the electric field strength. Right? Always good to write things down as we read them. If we move the particle 2 centimeters closer to the positive plate, so we're going to move it a distance of 2 centimeters, 2.0 centimeters. Determine how much work we need to do. And not a difficult problem. We can just go right into the formula that we derived right up here. QED. QED. We have the charge. And it's positive. Let's actually just make a note of that. The charge is positive, and then we are moving it closer to the positive plate, so we're going to have to do work to move it against the field. E is 1500, and D is 0.02. Multiply all those together, and you get the answer, which turns out to be 6.9 times 10 to the negative 5 joules, because work and energy are the same thing, and they're both measured in joules. Number 2, in the example above, determine how much electric potential energy the charge gained. Well, that's more of a theoretical question than anything, because of this formula here, work equals change in energy. In this question, the one above, we calculated the work, but work equals change in energy. So the answer to this question is exactly the same. Right? If it took us that much work, then that's how much energy it gained. And number 3, if everything else was kept the same, determine how much work you would need to do to move a 4.6 times 10 to the negative 6 charge. So we're hoping with this question that you're going to realize that 4.6 is just double the 2.3. And since in the formula it's a direct relationship, equals EQ D, since work is directly related to charge and work is directly related to the electric field strength and work is directly related to the distance, if you double the charge, then you're simply doubling, for the equation to remain in balance, you're simply doubling the work, right? If you double any of those values, then you're just going to double the work. So all you're going to do is take your answer from the previous question, 6.9 times 10 to the negative 5 and multiply it by 2. And it's going to come out to 1.4 times 10, because you only want two significant digits, times 10 to the negative 4 joules. So double. Okay, I've decided we're going to split this lesson up into two, because now we're going to talk about voltage, and voltage is a concept that we need to go over kind of slowly. So let's call it on 12-1 and move on to 12-2.